In this video, just some notes on how to get areas using integrals and some problems that you might run into and how to solve them. Very quick recap. To find the area of a region using an integral, we are going to be using definite integrals, and remember that these ones came from Riemann sums. This is the expression for a Riemann sum, and this is how it looks like. In Riemann sums, remember that we were using rectangles or other shapes to approximate the area of a function, and the function was f. The points that we used to actually get the rectangles were labeled xi, and this delta xi was just the length of the base of each rectangle. From here, we go to the definite integral if we allow the rectangles to be infinitely many and infinitely thin, and then we get the area under the curve under the function f. I wanted to point out that these dx that we see in these integrals, and that many people think that it's just there because it's not serving any purpose, it's reminiscent of this delta x. It's in the limit that this delta x becomes infinitely thin and these ones become infinitely many, that it becomes a differential. But anyways, this is just how we came from the Riemann sum to the definite integral. And the question now is, can we calculate the area between two curves? Graphically, it looks like this. Can we calculate the area enclosed in this region? And the answer is yes. The general expression to find that is a definite integral from some limits a to b of the difference between the two functions. Usually the one that goes first is the function that goes on top, and the other one is the function that goes always below. You know how to get it. You've watched the other videos. I'm going to just point out some problems that you have and that you could have when calculating areas with integrals. First, in general, we're assuming that we have the algebraic expression for the functions. We know how to express the functions, and we also are given the limits, or we know the limits. So that's the standard situations. We know the function in terms of x. We have a regular y of x function, and we have well-defined limits. Graphically, it looks like this. You have two functions, you have the algebraic expression for these functions, and you have the limits. You know that the region that you want to calculate the area of, it's enclosed between these two functions and in these two limits. So you just have to set up the integral like this. In this case, it's going to be a definite integral from the limit 0 to the limit 4. And remember that these functions are given in terms of x. The integral is formed with dx, and the limits run on x. Okay, so the first limit on x is 0, the second limit on x is 4, and that's it. The function that goes on top is this one. The function that goes always below, it's this one, so this one comes first. And if this is a fairly easy integral to solve, and if you do it, if you evaluate, you get the area is 10.66. Okay. Another version of the standard situation is when you have the functions in terms of x, just your regular y of x again, but the limits are defined as vertical walls. So you don't have the functions defining the region by just where they cross. For instance, they cross here, but the area that you want to calculate, the region that you want to calculate the area of is this one, that it's enclosed between the two functions and two vertical walls. But again, the vertical walls are the limits, and for this one you would have to just set up the integral between 0 and 2. Again, that's why I call this one standard situation version 2. Now for the problems. Problem number 1, that the functions that you're given are not in terms of the regular x, but y. So it's kind of the other way around. For instance, like these two. You have your two functions, you have your region, but the expressions, the algebraic expressions for the functions are given in terms of the y. The one that it's kind of left out is the x, like the one that it's solved for, it's the x. So what do? Well, you do exactly the same, but you set up your integral on y and using the limits for the y. So in this case, this is the integral that you set up. The integral goes from -1. Remember that we're looking at the y's now, so goes from -1 to 1 on y. So the differential is on y. The variables are y's, and the function that you put first in the integral, in this case, since you cannot define which one goes on top, it's defined to be the rightmost function. So in this case, it's this one that goes first, and you subtract the other one. If you don't do this, you're going to get an area that it's negative, and you will have to turn it positive at the end, but that's it. But try to put it in the right order from the beginning. If you calculate this one, which is again pretty easy to do, you obtain the area of the region. Problem number 2, that the limits are not defined. For instance, this. You're asked to calculate the area enclosed by these two curves, and this limit, you can guess that it's 0, 0, but you don't know this point. So if the limits are not defined, you have to first find them, and you can do that by solving the system of equations formed by the two by the two curves. So you have this expression, you have this other expression, form of system of equations, and solve it in any way you want, or in any way you can. In this case, it's easy to just subtract one from the other and then solve the remaining equation, and you will get two answers, -3,3 and 0,0. 0,0 is this one, and obviously -3,3 is this other one, which makes this number, this limit, -3, this other point over here 3, so the coordinates of this point are effectively -3,3. And now we know that the functions are given in terms of y, so for the setup of the integral, we will have to use the y's. So we will discard this one, and then we say that the y's go from 0 to 3. Therefore, the limits on the integral are 0, 3. Again, we're working on y. The rightmost function goes first, and then the other one. And you calculate the area, you simplify this integral, evaluate the integral, and the area turns out to be exactly 9. There's another problem in which the curves switch position and you have separate regions for the area. For instance, like something like this. So you have to calculate the shaded region, but it's not actually one region, it's separated in two parts, right? This one and this one. And the curves switch positions. You have the red one going on top of the blue one here, but then it reverses. And then the blue one goes on top of the red one, and then it changes again. So how do you choose which one goes on top of which? How do you set up your integral? You might be tempted to say, well, the first thing that I notice is the first thing that I saw was the red one going on top, so I'm gonna put the red one first, I'm gonna put the blue one later. This is a regular thing given in terms of x, a regular function. Your integral will be something like this, -2 to 2, function 1, function 2, red 1, blue 1. But if you actually simplify this and solve and evaluate, you'll get something like this. You'll get 0. And in this case, getting 0 is a good thing because you immediately notice something wrong, that something's weird. You clearly see that this area, you don't know what it is, but it's not 0. So there must be something that we did wrong. And the thing is that if you hadn't gotten the 0, then maybe you would have thought that this was okay, but it's not. And it's not okay because of this switching of positions. So the right way to calculate the area is to just remember that this is the integral that we're trying to get, but instead of going from -2 to 2, let's calculate the region separately from -2 to 0 first, and if you do that, you get an area of 8, and then let's calculate from 0 to 2, reversing the order of the curves because the curves have switched positions. So instead of having to evaluate to solve the integral for this expression, I'm going to change the order. And if you do that and solve, you obtain another 8. So the full area is going to be just the two results that you got, and you have to add them. Okay, so every time you have to calculate a region that it's not actually just one, that it's separated, or that the curves switch positions, you have to do it separately. Okay, and sometimes these problems might combine. For instance, maybe you don't know that this point is 0, 0. You don't know the limits for when one region ends and the other one starts, and you have to calculate it first.